Hello friends, welcome to lecture number 14 of this course on essential mathematics for machine learning. Today we will discuss about Gram-Schmidt process. It is a process from which we can transform a set of Li vectors to a set of orthogonal vectors, or in fact orthonormal vectors. Because you know, in many bases we require orthonormal bases, and therefore this process is really very important when you need those kind of orthonormal or orthogonal bases, because you can transform any basis to orthogonal or orthonormal using this process. So, first let me define the orthogonal sets. However, many times we have gone through this definition, but just to recall you that let V be a vector space with an inner product. So, basically V is an inner product space here, non-zero vectors V1, V2, Vk. So, these are k vectors from the inner product space capital V. They form an orthogonal set if they are orthogonal to each other. It means the inner product of Vi Vj equals to 0 whenever I naught equals to j. If in addition all vectors are of unit norm, that is the inner product of a vector Vi with itself equals to 1 for all I 1 to k, then it is called an orthonormal set, means V1, V2, Vk are forming an orthonormal set. Again, if you are having orthogonal set, then it will be linearly independent, but reverse is or converse is not true. So, if you are having a set of k vectors that is orthogonal, obviously those k vectors will be linearly independent. Now, you have seen this theorem already in orthogonal projection, but we have to recall it in a wider setting, means where we are talking about a subspace. So, let V be an inner product space and V0 be a finite dimensional subspace of V. So, what V is an inner product space and V naught is a finite dimensional subspace of V. Then any vector x belongs to V is uniquely represented as x equals to p plus o, where p is a vector in V0 and o is a vector which is perpendicular to V0, that is V0 complement. The component p is the orthogonal projection of vector x onto the subspace V0. The distance from x to the subspace V0 is given by the length of this vector O, because it is a perpendicular distance. So, obviously it will be distance from x to the subspace V naught. If V1, V2, Vn is an orthogonal basis for V naught, then you can calculate very easily P. So, P will become x V1 and the inner product of x with V1 upon V1 norm multiplied with vector V1, then inner product of x V2. So, what it is giving you the component of the vector x in V naught subspace. So, you can see by this graphic. So, you are having this vector x and this is the subspace V naught. So, what is P? So, P is the component of x in subspace V naught and O is the perpendicular component. So, I can write this x as P plus O, and that I can write it uniquely, where P is a vector in V naught, as you can see here in this V naught subspace, and O is perpendicular to P, or even all the vectors lie in the subspace V naught, and hence distance of x can be given by this, and that is the length of the vector O. So, these are some results which we have seen earlier also in the orthogonal projection lecture. Now, we will use these results to find out a process by which we can convert a set of linearly independent vectors to a set of orthogonal vectors, and that process is called Gram-Schmidt process. So, let V be an inner product space. Suppose x1, x2, xn is a basis of V. So, these are the vectors in V and they form a basis of V. So, better I write it in this way. So, x1, x2 and xn, since they are vectors. So, now since x1, x2, xn are basis of V, so they are linearly independent. Now, I want to convert this set of vectors containing the vectors x1, x2, xn into a set of vectors those are orthogonal. So, now let V1 equals to x1. So, whatever first vector you are having here, that I have written as such. Now, I want to make second vector V2 and I want that this vector V2 should be orthogonal to V1, that is your x1. So, for making it orthogonal, what I need? I need to subtract the component of in the direction of x1 from the vector x2, means whatever component of x2 is there in the direction of x1, if I subtract that from x2, then what will happen? After subtraction, whatever vector you are getting, that will be perpendicular or orthogonal to x1. So, I will use this concept only. So, V2 equals to x2 and now from x2 I will subtract the component of x2 that is in direction of x1. So, how I will do it? I will write like this: x2 V1 upon V1, V1 means I am subtracting in the direction of x1, that is your V1 only, into, so in the direction of V1, so into V1. So, if you notice, this is a component of x2 in the direction of V1 and I am subtracting this from x2. So, what? Now, V2 does not have any component in direction of V1, that is component in the direction of V1 is 0. Hence, V2 and V1 are perpendicular, that you can see here also. If you find out V1, V2, that will become V1 is your x1 and this is x2 minus x2 x1 upon x1 x1 into x1. So, this will become x1 x2 by this minus x1 x1 will be cancel out, x2 x1 and this is 0. So, inner product of V1 and V2 is 0. So, they are orthogonal. Similarly, I will go for third vector V3. So, V3 will be again I will subtract from x3 the component of x3 in the direction of V1 and V2. So, it will become x3 V1 upon V1 V1 into V1 minus x3 V2 upon V2 V2 into V 2, and I will go in the same way x 4 like that, and finally for V n I will be having x n minus x n V 1 upon V 1 multiplied with vector V 1 minus x n V 2 and so on, and finally I will be having x n V n minus 1 V n minus 1 V n minus 1 into V n minus 1. And as you have seen here, V 1 V 2 are orthogonal. Similarly, V 3 will be orthogonal to V 1 and V 2 and so on. Then what I can write, V 1 V 2 V n is an orthogonal set. So, this process of finding another set which is orthogonal from a given linearly independent set is called Gram-Schmidt process. Now, what is important here? Important is, since x 1, x 2, x n is a basis of V, so they span the vector space V. The question is whether this new set V 1 V 2 n is also spanning the vector space V. Yes, the span of x 1, x 2, x n equals to span of V 1 V 2 V n. We can easily prove it. So, what we have seen? Any basis x 1, x 2, x n, we apply the Gram-Schmidt process on it, and then we got the orthogonal basis. V 1, V 2, V n, where V 1 equals to x 1, V 2 equals to x 2 minus the component of x 2 in the direction of V 1. Similarly, V 3 will be x 3 minus the component of x 3 in direction of V 1 minus the component of x 3 in direction of V 2 and so on, like we have seen it on the previous slide. Now, some properties. So, first property is, here V k will be x k minus alpha 1 x 1 plus alpha k minus 1 x k minus 1 for 1 to k to n. As you, and what is alpha 1? Alpha 1 will be inner product of x k with V 1 upon V 1 V 1, inner product of V 1 with itself and so on. So, these are the scalar coefficients. Now, second is span of V 1 V 2 V k equals to span of x 1 x 2 x k, and this you can prove by this one easily by using this particular thing. The third one is V k is orthogonal to x 1 x 2 up to x k minus 1. Number 4, V k equals to x k minus p k. So, what I can write? where Pk is the orthogonal projection of the vector xk on the subspace spanned by x1, x2, xk minus 1. And what is this? The length of Vk, that is norm of Vk, is the distance, and what distance? Shortest distance. From xk to the subspace spanned by x1, x2, xk minus 1. So, we can make in this way. So, these are some properties very easy to remember and easily verify from the Gram-Schmidt process. Now, if you write like this, just the same process what we were doing, we are writing V1 equals to x1, and then what you do, you write W1 equals to V1 upon norm of V1. Then what you are doing, you are calculating V2. So, V2 you write x2 minus x2 with W1 into W1. So, what? The same thing, because W1 is having unit length. So, I am not writing denominator here. So, same thing which we have done earlier, only thing in terms of unit vectors. And then what you do, define W2 equals to V2 upon norm of V2. So, W2 again a unit vector, then V3 will become x3 minus x3 W1 multiplied with W1 minus inner product of x3 with W2 multiplied by with W2, and then W3 you define V3 upon norm of V3. If you go in this way, finally you will be having Vn, that is xn W1 multiplied with the inner product of xn and W1 with W1 minus, and finally inner product of xn with Wn minus 1 multiplied this scalar with Wn minus 1, and then define Wn equals to Vn upon norm of Vn. Then what you will be having, this set W1 W2 Wn span the same set which is spanned by V1 V2 Vn or x1 x2 xn, and it is a orthonormal set. So, in previous slide we have seen about orthogonalization process using Gram-Schmidt, but here we have just modified it in case when you need orthonormal set. So, now we will see some of the examples how to implement this process for finding the orthogonal or orthonormal basis. So, let us do example 1. So, let P be a plane in R3 spanned by the vectors x1 equals to 1 2 2 and x2 equals to minus 1 0 2. So, now first find an orthonormal basis for the subspace P, and the second thing, extend it to a basis of R3. So, we can solve this problem using two ways. One, first we will solve this one, that we will find an orthonormal basis for P using the Gram-Schmidt process on x1 and x2, and then we take a vector orthonormal to W and W2 which is coming using after applying the Gram-Schmidt process, and then it will become the basis of R3. Or you first take a Lie vector to x1 and x2, let us say x3, and then apply the Gram-Schmidt process. So, let us solve it. So, let x1, x2 and x3, which is you just take Li to x1 and x2. So, I am taking 0 0 1 be a basis of R3. So, I have added extend the basis of which x1 and x2 of P to a basis of R3. Now, so in fact it is not let here. Now, V1 will be your x1 and then W1 will become V1. So, what is norm of V1? It will become 1 9 square root 9 will be 1 by 3. So, 1 by 3 1 2 2. Then I will be having V2, that is your x2 minus x2 inner product of x2 with W1 multiplied with W1. So, here inner product is usual dot product in R3. So, x2 is minus 1 0 2 minus dot product of x2 with W1. So, minus 1 into 1 by 3. So, minus 1 by 3 plus 4 by 3. So, minus 1 by 3 plus 4 by 3, it will become 1. So, minus 1 times W1 and W1 is 1 by 3 1 2 2. So, minus 1 minus 1 by 3. So, minus 4 by 3 0 minus 2 by 3 and then 2 minus 2 by 3. So, 4 by 3. Now, calculate W2. W2 will become V2 upon norm of V2. So, this will become 16 by 9 plus 4 by 9 plus 16 by 9. So, 36 by 9. So, 4 and 4 square root will become 2. So, it will become 1 by 3 minus 2, because I have to divide by 2, minus 1 and 2. So, this is your W1 W2, and now W1 W2 forms an orthonormal basis of P. Now, what is orthonormal basis of R3? So, I will calculate V3. So, V 3 will become x 3 minus x 3 inner product with W 1 multiplied with W 1 minus inner product of x 3 with W 2 and that scalar multiplied with W 2. So, x 3 is here 0 0 1 minus inner product of x 3 with W 1 and so on, and after calculating it I will get 1 by 3 2 minus 2 1. So, that will be W 3. So, whatever V 3 I will get means I have to divide, means it will be 2 minus 2 1 and then W 3 will become length of this, that is 9 root 9. So, 1 by 3 2 minus 2 and 1. So, here this W 1, W 2 and W 3 forms an orthonormal basis of R 3. So, in that way we can apply the Gram-Schmidt process for finding the orthonormal basis for any subspace of a given vector space, or we can apply it for finding the orthonormal or orthogonal basis for a complete vector space, means vector space of any dimension, that is finite dimension, but not for infinite dimension. So, in this lecture we have learned how to solve or how to form an orthogonal or orthonormal basis for a vector space using the Gram-Schmidt process. In the next lecture we will learn another important decomposition of matrices, that is polar decomposition. In that decomposition what we usually have? We used to have a complex number like polar form of a complex number like a decomposition of a given matrix in form of an isometry and a positive definite matrix. So, thank you very much.